Okay, this is part 2 of going over the exam for like the third time, but that's a-okay. So calculate the mass of water that can be vaporized at its boiling point with 200 kilojoules of heat. So write down what you have, which is the 200 kilojoules. So, but I guess to start over, is the equation you're going to use is like joules equals moles times like whatever delta H is. So this is going to be delta H of vaporization, because when I boil, I'm vaporizing. So I'm going to sub in what I have, which is at 200 kilojoules, equal it to the amount of moles I have, but I don't have moles yet. So what I want to do is multiply it by 40.7, which is the heat of vaporization. So when I do that, I will get, can't even tell you at the moment. So basically I'm just going to divide the 200 kilojoules by that 40.7 to get 88.6 grams. So what I did in here was I just divided that number, so the 200 kilojoules by 40.7, and then multiplied it by 18.02, which is the molar mass of water. So in doing that, I was just able to get 88.6 right out the bat. So if you need to do the conversion and it helps, put 1 mole on the bottom, and then I times 18.82 on the top. So that's how I got D. So 12 is a substance has a normal boiling point at 62.4 degrees Celsius and a heat of vaporization at 30.1 kilojoules per mole. What is the vapor pressure at 50 degrees Celsius? So what I want to do is the 2-point Clausius-Clapeyron equation, which is going to be that ln of P2 equals, or ln of P2 over P1 equals negative delta H vape over R times 1 over T2 minus 1 over T1. So remember the normal boiling point is just going to be equal to the temperature at which it boils at 1 atm or 760 torr. You cannot use atm here because when you have ln of 1, it's going to be 0. So that just doesn't work. So start by writing out your equation, which I just recited from memory because I've done this like 4 times today, but that's okay. So start subbing in what you have. Remember that R on the bottom, that 8.314, is going to dictate my units, which is joules per mole times degree Kelvin. It's joule per mole times degree Kelvin. I just wasted a bunch of time trying to look it up. It's 8.314 times joules per mole degree Kelvin, which means that I need to have that delta H vape in joules, and I need to have my temperature in Kelvin. So that's incredibly important to have when you're solving the Clausius-Clapeyron equations, right? So, yeah, that's me after I confirmed it that I was right. Took time to do that. So start writing in what you have. So ln of P2 is what you're looking for. Yeah, that's just me just pointing to variables. Once again, very sorry, and I'm very tired. So I don't know P2, so I'm just going to put 760 on the bottom because that's my P1, that's my normal boiling point, equals that negative delta H vape. I need to convert kilojoules to joules, which is just multiplying it by 1,000 to get 30,100 joules, over that 8.314. And so what I'm going to do now is convert my temperatures to Kelvin, which is just adding 273. You're going to want to have the smaller temperature first, so in this case that 50 degrees Celsius converted to Kelvin, so that I end up with a positive number, because if I put that 62 degrees Celsius first, I'd end up with a negative number, right? So it's going to be 323, or 1 over 323 minus 1 over 335.4. So be careful with this math. I would do it out separately in your calculator, like do the 1 over 323 minus, then like the 1 minus 335, doing these separately and like writing them down, because people would having some issues. But from there, just do out the right side of the equation, so you get negative 0.414. So then you're left with that ln on the left side. So what you're just going to do is raise everything to the e. So e raised to the negative 0.414 on the right side, and doing that on the left side is going to get rid of that ln. So I'm just left with P2 over 760. Multiply that 760 over there in order to get, it's like 502 point, I think 16. Let's see. That I think is a 16. Anyways, it's close enough to 499.7. I did this in the spring, so I'm sure at some point I did get 499.7 torr, but just know that you 502 is also correct. So 13, how much heat is required to heat 42 grams of water from -8 degrees Celsius to 102 degrees Celsius. So this is where I'm going to have to be using my heating curve of water. So with the heating curve of water, there's basically 5 segments. I'm going to have heating, phase change, and heating again. So when you draw that out, well, basically what this problem is asking is just to add all of those heating and phase changes to get that total energy, because you have to take in consideration all the major events that happen. So like I heat, I phase change, I heat, I phase change, I heat, right? So because I know at 0 degrees Celsius I have freezing point, and at 100 degrees Celsius I'm going to have boiling point for water, right? So I just mark those points on my graph just to help myself out and make sure my say is organized. I would advise doing this on your test as well. So from here, if you're unsure of when to use Q equals MC delta T, it's going to be where that temperature is changing on those diagonal lines, right? Because that delta T just means change, right? And so that C values, by the way, are stuff that's going to have to be given to you or in some sort of table. And when I have those straight lines, I'm going to use moles times my heat of fusion or heat of vaporization. Those are also values that should be given to you, because they vary for compound to compound, so I wouldn't worry too much about that. So I just like writing up the information. So I use MCAT for my first step. My mass is 42 times 2.09, which is the heat capacity for ice, and it's joule per gram times Kelvin or degree Celsius, and then times the delta T. So delta T is just T final minus T initial. So my T final was 0 degrees Celsius, and I started out at -8 degrees Celsius, so 0 minus -8 is 8. So you just multiply it by 8. And I converted these to kilojoules just to make it easier on myself, just because, it's going to be really large numbers to work with the joules, and also my answer choices were in kilojoules. So 0.70224. So for segment 2, I'm going to use the heat of fusion, because I know at 0 degrees Celsius I have a phase change from solid to liquid. So I'm going to use moles times delta H. So I'm going to first convert moles of water into, mass of water to moles. So that's just 42 divided by 18.02. So when you do that, you should get 2.33, which I guess I'm going to rewrite out. So 2.33 times 6.02 kilojoules per mole. So that's already in kilojoules, so that makes it easy, and you should get 14.026. So 3, I'm just doing MCAT again, but using a different delta C different C and delta T. So 42 times 4.18, which is something that should also be given to you, times my temperature change. It started at 0, I end at 100, so it's going to be a change of 100 degrees. So you should get approximately 17.556. So for 4, it's vaporization, so 2.33 moles times 40.7 kilojoules per mole. And when you put that in your calculator, you should get 94.831 kilojoules. So I'm just going to go ahead and write those units out just so they're concise. And then part 5 is just doing the same thing again. I heat from 100 to 112. So I'm going to use 42 times 2.01, that's the heat capacity of gaseous water, water vapor, times 12. So when you multiply that together, you should get 1.013 kilojoules. So the total energy required is going to be the summation of all those steps. So when you add those all together, you should get 128.2 kilojoules. And for problems like these, I would also expect that, I guess I'm highlighting, you might want to expect that it might not be a full melting or like heating ice, melting ice, heating water, vaporizing water. It might just be heating water, vaporizing water, heating gas. Like the last three steps, which I'm writing up here. Like I said, like it might be like 56 to 102 or 120. And you would have to like account that I would not have those first two segments on the graph, right? Because I'm only going to have vapor or heating the liquid, vaporizing, and then heating the gas.